All right, so we are starting chapter 1 today, which is our first look at actual calculus. The section 1.1, the first section in chapter 1, is labeled a preview to calculus. This is sort of introducing the big ideas of calculus and really why we need calculus. So let's start off. There's basically two components that we're going to be talking about today. The first is dealing with tangent lines. Now, up until calculus, we could find rates of change as long as the rate of change didn't change, as long as it was a constant. So for instance, if I had a scenario where it cost me a certain amount to set up the design for a t-shirt, and then each t-shirt cost me $12 on top of that, I would get a line, and I could tell you the rate of change for that entire situation was $12. And I didn't need calculus for that. However, let's say we had a scenario where we have an object moving and we're just looking at its distance to a certain point, and this is a very common calculus thing, and its distance as it moves away, right, is changing. So we have an object that moves away, it actually comes back and then moves away again, okay? And in this case, let's say we want to know what the rate of change is. In other words, the velocity or the speed. So what we'd be looking at is let's say we wanted to know the speed at this particular point, right? Well, we would need to find the slope of the tangent at that point. Now, the problem with this is ever changing. So if I find the slope here, it's going to be different here. Up until now, we haven't been able to deal with that. So this is where we're going to start our discussion here, is with the tangent line problem. Okay, so the tangent line problem is sort of an easy one to lay out here. If we had a scenario, let's just say that we wanted to find the slope of, let's make it really basic, y equals x squared, and we were interested in knowing what the rate of change is, or the slope at x equals 1. So let's take a look at this. Okay, so let's say we're interested in the slope there. Now we clearly know that there's a slope there, we can see it, and we could even draw it. This is what's called the tangent line. And what we're interested in is the slope of that tangent line. Okay, so we know this line exists, we know that the slope exists, but the question is, how are we going to find that? So the problem is with sort of algebraic, our algebraic use of, or understanding a slope is problematic, because when we think of algebra, how do we do slope? We do rise over run, or delta y over delta x. The problem here is, if I only have one point, we get nonsense here. If we have 2 points, no problem, we find the 2 points. As long as they're not vertical, we're going to have a value that makes sense here. When it's 1 point, if you think about it, our change in y is 0, our change in x is 0. So that's nonsense, that's not helpful, okay? So an algebra understanding of this is not going to work. Before we get to the calculus, what we're going to do is we're actually going to look at approximating this slope. So before we actually understand the calculus, we're going to approximate this slope. So what I want to do is, I want to look at what is called the secant line. Okay, so the secant line is 2 points. And we're going to find the slope of the secant line. All right? So, for instance, let's say I took, let's say we zoom in on this. Let me erase this. Struggling here with my markers. And really, let's say we're interested, and this is not going to be to scale or anything like this. We're interested in this value here. Okay, so let's say we don't quite have the math yet to find the exact value, but let's say we find an approximation. So let's say we go with 1.5. Okay, so what we're going to do is we're going to take a point here and we're going to go 1.5. So let's keep track of this. So we have f of x, okay? So we have 1, 1, and then let's say we do 1.5 to f of 1.5. So that's 1.5 squared. So that is 2.25. Okay, well now I can find an approximation. So an approximation for this rate of change would be 2.25 minus 1 over 0.5. And we get 2.5. So if we go 1 to 1.5, we get an approximation of 2.5. All right? Now, maybe we're sitting here going, that isn't a very good approximation. Let's go with 1.1. And like I said, this is not to scale. I'm just giving myself some room here. So let's say we go with 1.1. Okay, now what you see here is this tangent line, or excuse me, this secant line is sort of getting closer to that original tangent line if we sort of imagine that. So let's go ahead and do that with 1.1. So now we have 1.1 squared, and that's 1.21. Okay, so now let's go ahead and do the rate of change from 1 to 1.2. So this will be 1.21 minus 1 divided by 0.1. And now we get an approximation here on this one of 2.1. Okay? Now let's keep going. Let's go with 1.01. So 1.01, closer still, once again, nothing to scale here. We get 1.01. So let's say that's right here. And now you can see that 1.01 is so close together that even with me changing that scale, are so close together that that secant line is almost the tangent line. So 1.01 squared is 1.0201. And now I'm going to do the rate of change from 1 to 1.02. So minus 1 divided by 0.01, and we get 2.01. I'm not even going to try to do the next one, but basically each one of these approximations is getting better and better and better and better. Okay, so essentially what we're doing is the idea with the tangent line problem is we can't get the slope of that tangent line directly with one point. But what I can do is do the slope of various secant lines getting closer and closer and closer. Each new approximation is a better approximation. Let's just do it one more time with something very, very close. So let's just go with 1.001. And we could just keep going with this, getting closer and closer and closer. To some extent, it'll become kind of overkill. So 1.001 squared. We get 1.0020001. So let's take that. We're going to subtract the 1, right? So I'm just doing, understand here, I'm just doing standard slope here. Don't be confused. I'm just doing what I did here, rise over run, algebra 1 style. And then I'm going to divide by 0.001. And what I get is 2.001. So we go from 2.5 to 2.1 to 2.01 to 2.001. I think what you'll find is, and what you can almost guess is, this approximation is getting closer and closer to 2. Later we will have the math to actually confirm that the slope of our tangent line is actually equal to 2. Right now, let's leave it as an approximation because we're not using strict calculus analytics. So the slope of that line is 2. So for the time being, we're going to look at this as just approximating using the slope of secant lines to get the slope of the tangent line, using points that get closer and closer together. Okay? I'm going to go ahead and draw up the math for this here in a moment. Okay, So now we're going to talk about the tangent line problem sort of in a general sense. So we don't want to tie it to a function like x squared at point 1. Let's say we have the function f of x, and let's say we're interested in the tangent line at some unknown value, but a constant c. So once again, we can't find the slope of that tangent line directly because we don't have calculus skills, and algebra skills are going to give us nonsense. So I get a second point, okay? And we do instead the slope of the tangent line, we do the slope of the secant line to approximate the slope of the tangent line. So this right here we're going to call x plus delta x. Sometimes some books will use instead of delta x, because delta x does get a little cumbersome, sometimes books use x plus h. Just know that that means the same thing. Our books use delta x. So this would be f of x plus delta x. So if I want to approximate the slope of the tangent line at C, so we're going to approximate slope of tangent line at x equals C, okay? What we're going to do is we're going to use these 2 points that I've gotten here. So this is going to be, the y's will be, subtract the y's, so this will be f of x plus delta x minus f of c over, and then we're going to subtract the x's, right? Just like we do Algebra 1 style. So x plus delta x minus x. Now you'll notice we can do a little simplifying here, and this will always work out this way. The x's are going to subtract in the denominator, and what I'm left with is f of x plus delta x minus f of c over delta x. This is going to be our approximator, okay? And the thing we want to understand about this is the smaller we choose x to be, or excuse me, the smaller delta x, the better approximation. So if you remember from my example before, we start with a delta x of 0.5, and then we went to 0.1, and then we went to 0.01, et cetera, et cetera, et cetera, and our approximation got better and better. Eventually, once we start learning our calculus, we'll be able to find the exact using a tool called limits, which is what this chapter is all about, okay? So that is the first big concept of calculus, and that all comes from this tangent line problem. Now we're going to talk about the second big problem of calculus, which is kind of good news. Really, when it comes down to it for this course, is we have 2 major concepts. We just have to understand those major concepts very well.